There is a place in our galaxy where nothing appears to happen. No light, no movement, no sound. Just an enormous cloud of cold, dark gas, drifting silently through space, as it has been drifting for millions upon millions of years. From the outside, it looks like absence, like a wound in the fabric of the night sky. A darkness that is somehow darker than the darkness around it, blotting out the stars behind it, swallowing their light before it can reach us. Ancient astronomers looked at patches like this and thought they were simply gaps, holes in the heavens where no stars had been placed. They did not realize they were looking at something far more interesting than emptiness. They were looking at the beginning of everything, because that darkness is not empty. It is full of hydrogen, full of helium, full of dust, full of the scattered ashes of ancient stars that burned and died long before our sun ever existed. Full of potential so vast, so patient, so quietly immense, that it will, in time, become one of the most extraordinary things the universe knows how to make. A star, not a distant point of light you glance at on a clear night and move on from. A living, burning, furious ball of nuclear fire, powerful enough to warm planets across hundreds of millions of miles of empty space, powerful enough to bend the paths of comets, powerful enough to anchor entire solar systems to itself. For billions upon billions of years, through nothing more than the invisible reach of its gravity. And it begins here, in the dark, in the cold, in the silence. Tonight, we are going to follow that journey from the very beginning, from the first stirring in a cold molecular cloud, through the long, slow process of collapse, through the formation of a protostar buried in its own dusty cocoon, all the way to the moment a star ignites for the first time and floods the universe with light. There is no rush. This story has been unfolding for longer than the Earth has existed. It is a story told in millions of years, in light years, in temperatures so extreme they have no equivalent in ordinary human experience. And yet, at its heart, it is a deeply simple story. Something that was not, becoming something that is. Potential becoming reality. Darkness becoming light. Find a comfortable position. Let your body settle. Let your breathing slow. And let the universe show you something it has been perfecting since long before there was anyone here to watch. The birth of a star. Before any star can exist, before any light can be born, there must first be a cloud. Not a cloud you would recognize, not the soft white formations that drift across a summer sky, catching the afternoon light and casting gentle shadows on the ground below. Not the heavy gray weight of a storm front rolling in from the sea. This is something altogether different, altogether older, altogether more immense. Astronomers call it a molecular cloud, but perhaps a better name would simply be a nursery, a cradle, a place of extraordinary patient waiting, where the raw ingredients of the universe are held in a cold and quiet suspension, waiting for the conditions that will allow something entirely new to be made from them. These clouds are among the largest structures in the galaxy. A single one can stretch for 2, 3, sometimes 500 light years from one edge to the other. To put that in some kind of human terms, light, traveling at 186,000 miles every second, would take 300 years to cross from one side of such a cloud to the other. Our entire solar system, the Sun, all 8 planets, the asteroid belt, the Kuiper belt, the distant ghostly realm of the Oort cloud at its outermost edge, all of it would be an invisible speck somewhere inside. Not a large speck, not even a meaningful speck, an invisible one. And yet, despite this incomprehensible scale, the molecular cloud is almost unimaginably cold, roughly 10 degrees above absolute zero, colder than anything that naturally exists on Earth. Colder than the surface of Pluto, colder than liquid nitrogen. A cold so deep and so complete and so absolute that even the atoms inside barely vibrate. They move only in the sluggish, minimal way that thermodynamics requires, and no more. They are as close to perfectly still as nature allows anything to be. It is dark, cold, enormous, and ancient. And it is where everything begins. What exactly is inside this cloud? Mostly hydrogen, the simplest, oldest, most abundant element in the universe. The element that was forged in the first few minutes after the Big Bang itself, when the newborn universe had cooled enough to allow protons and electrons to combine for the first time. About a quarter of the cloud's mass is helium, the second simplest element, also forged in those first few fiery minutes of creation. And then, scattered thinly through both, something extraordinary: dust. Not ordinary dust, cosmic dust. Grains smaller than the width of a human hair, made of carbon and silica and ice and complex organic molecules, floating through the gas in a vast, slow, barely perceptible suspension. These grains are so small and so thinly spread that if you scooped up a cubic kilometer of the molecular cloud, the total amount of solid material you would find inside it would fit comfortably in the palm of your hand. And yet this dust is crucial. It is the seed of planets. It is the building block of worlds. And it carries within it a history longer than anything on Earth. Here is the remarkable thing about that dust. It is not new. It is not freshly made. Those tiny grains drifting through the cold dark of this molecular cloud are the ashes of stars that no longer exist. Stars that blazed and burned and eventually exploded, some of them, billions of years before our own sun was born. In the violence of those ancient stellar deaths, every heavy element those stars had spent their lifetimes forging, every atom of carbon, oxygen, iron, calcium, silicon, every element heavier than helium, was scattered outward into space in great expanding shells of superheated gas. Those shells cooled over millions of years. The atoms within them slowed. They found one another. They stuck together. They formed grains. And those grains, over the immensity of time, found their way into clouds, just like this one. Which means the raw material waiting inside this molecular cloud has already been a star, perhaps more than one. It lived and burned and died and was scattered across the light years and drifted through the dark for an almost incomprehensible span of time. And now, here it is again, patient, cold, waiting to become something new. There is something quietly profound in that. The universe does not waste its material. It does not discard what it has made. It recycles, transforms, begins again. The ash of an old fire becoming the fuel for a new one. Death folded back into birth with the patience of geological time. And it is worth pausing here, just for a moment, to note something that may feel strange to hear, but is simply a matter of chemistry. You are made of this same material. The calcium in your bones, the iron in your blood, the carbon that forms the molecular backbone of every cell in your body, the oxygen you are breathing right now, none of it was made on Earth. All of it was forged inside stars. Stars that lived and burned out long before our solar system existed. in parts of the galaxy we will never visit, whose light has long since faded. Those stars exploded, their material scattered. It drifted through space for millions of years, gathered into clouds, collapsed into new stars, seeded planets, and eventually, through a chain of events so long and so complex that no one has yet traced it in full, became the world you were born on, and the body you were born into. You are, quite literally, made of stardust, not as a metaphor, not as a poetic turn of phrase, as a fact of nuclear physics and stellar chemistry. The cloud above us contains the same ingredients, the same ancient material, the same patient, quiet potential. So here, in this vast, dark cloud, we have everything we need. We have the hydrogen and helium. We have the ancient cosmic dust. We have billions of years of accumulated stillness. All that is missing is the moment something changes. For a very long time, nothing happens. That is not a dramatic overstatement. The molecular cloud genuinely does nothing for immense stretches of time. Millions of years pass, tens of millions, and the cloud drifts through the outer arms of the Milky Way, cold and dark and still, giving no outward indication that anything is about to change. If you could somehow watch it from the outside, accelerating time so that 1,000,000 years passed in a single breath, it would look, for most of its history, exactly as it does right now. Dark, still, patient beyond any human reckoning. To understand why change is so slow to come, and to understand why it eventually becomes inevitable, you have to understand the forces at work inside the cloud. Because the cloud is not truly static. It is held in a kind of dynamic tension, a balance maintained by competing forces that push and pull against each other across distances that dwarf anything in our solar system. The first force is gravity. Gravity is always present, always patient, always pulling inward. Every particle of gas in the cloud exerts a tiny gravitational attraction on every other particle. The cloud, as a whole, is constantly trying to pull itself together, to compress, to collapse inward toward its own center of mass. Gravity does not get tired. It does not relent. It simply waits, applying its quiet force across every cubic centimeter of the cloud's vast interior at every moment of every year of every 1,000,000 years of the cloud's long existence. But gravity has an opponent. Thermal pressure, the energy of the gas itself, pushes outward. Every atom in the cloud is moving, even in this extreme cold, even at 10 degrees above absolute zero. The atoms are not perfectly still. They vibrate, they drift, they collide with their neighbors. That microscopic, barely there movement generates pressure. And that pressure pushes outward in every direction, resisting the inward pull of gravity with a force that is, for enormous stretches of time, almost exactly equal to it. The result is a standoff, gravity pulling in, pressure pushing out, neither winning. The cloud neither collapses nor expands. It simply holds, balanced on an invisible fulcrum, drifting through the galaxy in a state of equilibrium that can last, in the right conditions, for tens of millions of years. There is a third force involved as well, one that is harder to visualize, but equally important in maintaining this long, patient balance. Magnetic fields thread through the molecular cloud like invisible rivers, winding through the gas in long, curving, complex lines that follow no simple geometry. You cannot see them. No optical telescope can photograph them directly. but they are there, real and measurable, and they act as a kind of hidden scaffold, a structure embedded within the cloud itself that helps support it against gravitational collapse, threading through the denser regions of gas and helping to slow the process, drawing out the silence by years, by centuries, by millions of years. These three forces together, gravity, thermal pressure, and magnetic support, create the conditions for the long waiting that defines this period. In astrophysics, the moment when gravity finally overcomes thermal pressure and collapse becomes inevitable has a formal name. The Jeans instability, named after the British physicist Sir James Jeans, who worked out the mathematics in the early 20th century. He calculated precisely the relationship between a cloud's mass, its temperature, and its density, and derived the threshold, now called the Jeans mass, above which a cloud or a region of a cloud will inevitably collapse under its own gravity. But the mathematics, precise and elegant as they are, perhaps miss the more human truth of what this period is. It is a waiting, not an anxious waiting, not the waiting of something that wants to move but is held back. Something more like the waiting of deep soil in winter, something accumulating beneath the surface, in silence, with no visible sign, for as long as it needs to. Within the cloud's vast interior, it is not perfectly uniform. There are regions of slightly greater density, places where random currents and eddies in the gas have, over the long centuries, nudged a little more material together. These denser regions have slightly stronger gravity than the regions around them. They pull in a little more gas. They become a little denser. Their gravity grows a little stronger. It is a slow, incremental process, playing out over timescales that are almost impossible to relate to anything in ordinary human experience. But it is real, and it is happening, and it is the quiet planting of seeds that will, in time, become stars. And then, eventually, the balance breaks. Something disturbs the cloud. It might be a shock wave from a distant supernova, one of the galaxy's dying massive stars detonating in a colossal explosion and sending a pressure wave rippling outward through space, passing through the cloud like a gentle but irresistible hand pressing against a soap bubble. It might be the slow tidal influence of a passing star cluster or a nearby spiral arm. It might simply be that one of those dense knots inside the cloud has grown massive enough over millions of years of slow accumulation that its own gravity has finally crossed the gene's threshold. Whatever the trigger, the balance tips, and the long silence ends. When a region of the molecular cloud begins to collapse, it does not do so all at once, and it does not do so cleanly. It begins with a single region, a knot of slightly denser gas, perhaps a few light years across, reaching that critical threshold where gravity finally and definitively wins. And then it begins to fall inward, slowly at first, almost imperceptibly. The atoms of hydrogen at the edge of the collapsing region begin to move fractionally faster toward the center. The density at the core begins to rise. The process is so gradual that if you could somehow observe it in real time, you would notice nothing. You would have to watch for thousands of years to see any measurable change. But gravity accelerates everything it touches. As the gas falls inward, it becomes denser. As it becomes denser, the gravitational field at the center grows stronger. As the gravitational field grows stronger, the gas falls faster. The collapse feeds itself in a slow but self-reinforcing cascade, each increment of density leading to a stronger pull, each stronger pull drawing in more material, each additional material increasing the density further still. This is gravitational collapse. It is one of the most fundamental and consequential processes in the universe. It is the mechanism by which the diffuse, spread-out material of the interstellar medium is concentrated into the dense, hot, brilliant objects we call stars. Without gravitational collapse, there would be no stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no planets, no chemistry, no life. Everything begins here, in this slow fall inward. As the gas compresses, something else begins to happen that will become central to the rest of this story. Compression generates heat. This is a fundamental principle of thermodynamics that you can feel in everyday life. A bicycle pump grows warm when you compress air through it. A diesel engine ignites its fuel through compression alone, without a spark. What is happening inside this collapsing region of the molecular cloud is the same basic physics, but on an astronomical scale. The temperature at the core begins to climb. From the cloud's ambient 10 degrees above absolute zero, it rises to hundreds of degrees as the collapse progresses. Then thousands, then tens of thousands. The gas, which was dark and invisible and radiating no detectable light just a short time ago in cosmic terms, begins to glow. First in the far infrared, at wavelengths far too long for human eyes to detect, but measurable by the right instruments. Then, as the temperature rises further, in the near infrared, a warmth appears at the center of the collapsing region, very faint at first, detectable only as a slightly elevated temperature in an otherwise cold cloud. There is, for the first time in this story, something that could be called a center, a focal point, a concentration of matter and energy around which the rest of the collapsing cloud is organizing itself. Astronomers call this object a protostar. It is not yet a star in any complete or meaningful sense. It has not yet ignited the nuclear reactions that define a true star. It cannot yet balance itself against gravity through its own energy output. It is, in the most honest terms, simply a hot, dense, rapidly growing ball of collapsing gas. A seed pressing through the dark towards something it does not yet know how to be. But it is growing quickly. Material is falling inward from all directions, adding to the mass at the center, compressing it further, heating it further, building both its density and its temperature with every passing year. Around this protostar, something equally remarkable is beginning to take shape. The collapsing cloud does not fall inward in a perfectly symmetrical, perfectly radial way. It has rotation. Every molecular cloud has some small amount of angular momentum. A slow, barely perceptible spin inherited partly from the large-scale rotation of the galaxy itself, partly from the random swirls and eddies of gas within it. Under ordinary circumstances, this rotation is so slow as to be nearly undetectable, but as the cloud collapses and material falls toward the center, something important happens to that rotation. It speeds up. This is the same physics that makes a spinning ice skater rotate faster when she pulls her arms inward. She is not adding energy to the system. She is simply redistributing it. By bringing her mass closer to her axis of rotation, she reduces her moment of inertia, and conservation of angular momentum requires that her rotational speed increase in exact proportion. The same principle governs the collapsing cloud. As material falls inward toward the growing protostar, it brings its angular momentum with it, and the rotation of the inner region speeds up accordingly. As the rotation speeds up, it begins to resist the inward collapse. Material falling toward the protostar feels a growing centrifugal effect. Gas falling directly onto the poles of the protostar along the axis of rotation can continue inward relatively easily. But gas falling toward the equator is deflected sideways. It cannot fall directly inward. The rotation is moving it too fast. Instead, it spreads outward along the equatorial plane, flattening into a rotating disk around the protostar's middle. This is the protoplanetary disk, one of the most significant structures in planetary science. It is the channel through which material spirals inward to feed the protostar's growth, and it is simultaneously the raw material from which, given sufficient time and the right conditions, entire planetary systems can form. The same disk that is, right now, feeding the birth of a star will eventually, over tens of millions of years, give rise to worlds. Dust grains colliding and sticking together, growing from microns to centimeters to meters to mountains, accumulating through a hierarchy of collisions and gravitational gatherings into the full-scale planets, moons, asteroids, and comets of a solar system. Every rocky planet you know of began in a disk like this one. Meanwhile, at the poles of the protostar, perpendicular to the plane of the disk, something spectacular is being launched outward into space. Jets of superheated, magnetically accelerated gas shoot away from the forming star along its rotational axis. These are the bipolar outflows, one of the most visually dramatic phenomena in the process of star formation. They extend for light years in both directions from the protostar, glowing in the wavelengths of ionized hydrogen, punching glowing tunnels through the surrounding cloud, illuminating the dark material they pass through with a ghostly, ethereal light. These jets serve an important function. They carry away angular momentum from the protostar, acting as a kind of release valve that allows the star to continue accreting material without spinning itself apart. They are also, in a sense, the protostar's first communication with the wider universe, its first physical effect on the cloud that surrounds it, the first sign, visible across light years, that something new is being made here. The cloud around the forming protostar is no longer cold and silent. It is alive with heat and motion and the slow, immense violence of creation. And at its heart, buried in its own warm cocoon of gas and dust, a protostar is growing toward a threshold that will change everything. The protostar is still hidden from view. You would not be able to see it, even if you were close enough to try. The collapsing cloud that gave it birth still wraps around it like a thick, dense shroud, layer upon layer of gas and dust, opaque to visible light, impenetrable to the eye. The protostar sits at the center of its own cocoon, invisible to ordinary observation, known only by the infrared warmth that seeps outward through the surrounding material and can be detected by telescopes sensitive to those longer wavelengths of light. But it is growing. Every second of every day of every year of its long gestation, more gas spirals inward through the protoplanetary disk, adding to the mass at the center. And as the mass grows, so does the temperature. And as the temperature grows, so does the pressure pushing outward from the core. And as the pressure grows, so does the rate at which the infalling material is heated on impact, releasing energy, contributing further to the warming of the interior. This is the period astronomers designate as the Class 1 protostar phase, one of a sequence of classifications that tracks a forming star's evolution from deeply embedded object to visible young star. It is not a brief episode. This phase can last for hundreds of thousands of years. And during all that time, the protostar is doing one thing above all others: feeding. The accretion disk is the mechanism of that feeding. Material in the disk does not fall straight inward. The same rotational dynamics that created the disk keep it in a kind of slow, downward spiral. Gas and dust orbiting the protostar and gradually losing energy to friction and magnetic coupling with their surroundings, slowly descending toward the center over thousands of orbits. When material finally reaches the innermost edge of the disk and impacts the surface of the protostar, it arrives with enormous velocity. That velocity is converted into heat and light in a bright, energetic shock. At the height of the accretion process, a forming protostar can radiate more energy from this infalling material alone than our fully formed nuclear-burning sun produces from fusion. Not because the physics are inherently more powerful, but because the sheer rate of material arrival, the relentless, constant infall, generates staggering amounts of energy. At the same time, the bipolar jets we described in the previous chapter are performing a critical service. They are bleeding away angular momentum. Every kilogram of gas they carry away from the protostar is a kilogram of spin that is removed from the system. Without this continuous release, the protostar's rotation would accelerate as it gathered more material, faster and faster, until centrifugal forces tore it apart before it ever had the chance to become a star. The jets prevent this. They give the protostar room to grow, carrying away the excess rotation with them as they punch through the surrounding cloud at hundreds of kilometers per second. There is something that feels, at least metaphorically, almost organic about all of this. The protostar breathes in through its disk and breathes out through its poles. It feeds and it regulates. It draws the surrounding cloud into itself and simultaneously pushes material away. It is a dynamic, self-regulating system that balances multiple physical forces against each other with a precision that took human scientists decades of observation and calculation to fully understand. Deep inside the cocoon, the temperature at the core continues its long climb. Hundreds of thousands of degrees, millions. The hydrogen at the center, which at the beginning of this story was a cold, quietly drifting gas, is now a plasma, electrons stripped from their nuclei, bare protons and bare electrons moving at enormous velocities through a sea of heat and pressure. The density is rising, the temperature is rising, and with every passing century, the conditions at the core are drawing closer to a threshold that has defined the birth of every star that has ever existed. Then something shifts in the balance of forces. The protostar has grown energetic enough that its radiation, the light and heat streaming outward from its hot surface, begins to push back against the material still infalling from the surrounding cloud. Its stellar wind, a constant outflow of charged particles from its surface, grows stronger. The accretion begins to slow. For the first time, the protostar is fighting back against the cloud that made it. Slowly, over tens of thousands of years, it begins to win that fight. The dense cocoon around it starts to thin. The constant outward push of radiation and wind begins to excavate a cavity in the surrounding material. Slowly, holes and gaps appear in the shroud, and through those gaps, for the very first time, light escapes. The protostar is becoming visible, not to human eyes, not yet perhaps, but in principle, for the first time since it formed, there is light coming outward from this object that is not simply infrared warmth diffusing through dust. There is actual light reaching outward through the holes in the cocoon, illuminating the surrounding cloud from within. What you would see, if you were watching from a suitable distance and a suitable instrument, is something genuinely extraordinary. A young stellar object surrounded by the glowing remnants of its birth cloud, trailing wisps and streamers of illuminated gas and dust. The disk still visible as a dark silhouette against the light, the jets still firing in long, luminous columns. A thing in the process of becoming, caught halfway between the darkness it came from and the brilliance it is heading toward. The universe has been building this object for hundreds of thousands of years, and it is not finished yet. But for the first time, it has a presence. It has a face. There is a moment, and calling it a moment is perhaps misleading, because it unfolds not in seconds but over years and decades, when the long process of becoming reaches its conclusion. The protostar's core has been climbing in temperature for hundreds of thousands of years. Slowly, relentlessly, one increment of pressure and heat at a time, it has been building toward a threshold that exists in the fundamental physics of atomic nuclei. And now, at last, it reaches it. 10 million degrees Kelvin. At this temperature, the protons at the core, the bare hydrogen nuclei stripped of their electrons by the intense heat hurtling through the plasma at extraordinary velocities, are moving fast enough and are packed closely enough together that something changes when they collide. Under ordinary conditions, two protons approaching each other are repelled long before they can touch, pushed apart by the electromagnetic force that acts between two positive charges. At the temperatures of everyday experience, even the temperatures of the hottest stars' surfaces, this repulsion is insurmountable. The protons simply cannot get close enough together for anything to happen, but at 10 million degrees, they can. Moving fast enough, two protons can approach each other closely enough that a different force takes over. The strong nuclear force, one of the four fundamental forces of nature, extraordinarily powerful at very short ranges but falling off almost to nothing at larger distances, reaches out and grabs them. And when the strong force grabs two protons, it does not let go. They fuse. In the process, one of the two protons converts into a neutron, releasing a positron, the antimatter counterpart of an electron, and an almost massless particle called a neutrino, which shoots away from the reaction at very nearly the speed of light. What remains is a nucleus of deuterium, heavy hydrogen, containing one proton and one neutron, bound together by the strong force. That deuterium nucleus almost immediately collides with another proton and fuses again, forming a nucleus of helium-3, containing two protons and one neutron. And when two helium-3 nuclei find each other and collide, they fuse into a single nucleus of helium-4, the stable, ordinary helium that makes up a quarter of the ordinary matter in the universe, and release two protons back into the mix to begin the cycle again. This is the proton-proton chain, the nuclear fusion reaction that powers the vast majority of the stars in the universe, including our own sun. And it has just ignited for the first time inside this object. The energy released by each individual fusion event is tiny in absolute terms. But in the core of a newly ignited star, these events are not rare. They occur at a rate so high it is difficult to express in ordinary numbers. Hundreds of trillions of reactions per second, each one releasing a small packet of energy in the form of gamma rays that bounce and scatter their way outward through the stellar interior, taking thousands of years to work their way from the core to the surface. The total power output is enormous. In terms of energy per second, a star like our Sun produces the equivalent of detonating roughly 90 billion megatons of nuclear explosive every single second. It has been doing this for 4.5 billion years. It will continue for another 5 billion at least. And critically, this energy pushes outward against the weight of all the material above it, against the enormous inward pressure of gravity, against the force that has been trying to collapse this object since the very beginning of its story. For the first time in the entire history of this growing, collapsing, warming protostar, there is an outward force at the core that is powerful enough to completely balance the inward force of gravity. The collapse stops, not because the star ran out of material to fall inward, not because some external force intervened, but because the star itself has lit a fire powerful enough to hold itself up. It has, through the initiation of nuclear fusion, achieved what physicists call hydrostatic equilibrium, a state of balance between the inward pull of gravity and the outward push of radiation pressure that will be maintained with extraordinary precision for billions of years. This is the moment. This is the line between a protostar and a true star. This is what it means to be born. The energy flooding outward from the newly ignited core now strikes the outer layers of the star and is released into space as light and heat and radiation across the electromagnetic spectrum. It reaches the surrounding cloud and illuminates it from within. The gas that has been the star's nursery for hundreds of thousands of years begins to glow and scatter and be pushed slowly outward by the pressure of the young star's radiation. This early, energetic phase of stellar life is called the T Tauri stage, named for a well-studied young star in the constellation Taurus. T Tauri stars are dramatically, almost violently active by the standards of mature stars. They vary in brightness, they flare, they drive powerful stellar winds that sweep outward through the surrounding cloud, pushing the remaining birth material further and further away, carving an ever-expanding bubble of cleared space around themselves. They are not yet the calm, steady, middle-aged stars of the main sequence. They are young. They are turbulent. They are, in every sense, new. And they are announcing their existence to the universe in the loudest possible way, with light, with heat, with the fierce, uncompromising declaration of something that was not, becoming something that most definitely is. Over the next few million years, the young star settles. The fierce activity of the T Tauri phase gradually subsides as the remaining birth cloud is swept away and the accretion of new material slows and finally stops. The stellar winds weaken from a gale to a steady, gentle flow. The flaring becomes less frequent, less intense. The star, no longer gaining mass and no longer surrounded by the dense material that made its early life so turbulent, begins to find a rhythm. That rhythm is fusion. Hydrogen burning steadily at the core, gravity pressing inward, radiation pressure holding outward. The two balanced against each other in a state of equilibrium so precise, so stable, so enduring, that it will continue without fundamental interruption for billions of years. The star has arrived at what astronomers call the main sequence, not a place, but a state of being, a long, stable chapter of a star's life during which it is simply burning hydrogen into helium and shining. And now, for the first time in this entire story, we can simply look at it. It is, from a great distance, a point of light, warm and steady and quiet. Not remarkable at first glance, just another star among the billions that scatter the night sky of the Milky Way. But look at it with the knowledge of what it took to become this, and it is one of the most extraordinary objects in the universe. That light crossing the distance between us has been traveling since it left the star's surface. It left the surface as the product of gamma-ray photons that were themselves generated in the core, bounced and scattered through the interior for tens of thousands of years before they finally worked their way to the outer layers and were released as visible light. The photon reaching your eye has been traveling in one form or another since the star was young. It carries within it, in some deep physical sense, the memory of the fusion reaction that created it. If there were a planet around this star, a rocky world at the right distance, warmed but not scorched by its light, life might one day arise there. The planet's days and nights would be set by the star's light. Its seasons would be governed by the tilt of its orbit. Its oceans and its weather and the slow drift of its continents would all be driven, ultimately, by the energy this star puts out. The star would be the center of everything for anything that lived there. They might even have a word for it. They might call it the sun. And it is not alone in the sky of whatever worlds orbit it. Back in the molecular cloud from which this star formed, other pockets of gas were also collapsing, also growing their own protostars, also building toward their own ignitions. Star formation rarely happens in isolation. The same trigger that started this collapse likely initiated others nearby. The same cloud that gave birth to this star probably gave birth to dozens of others in the same general era, scattered across a region of space tens of light years across. Together, these young stars form what astronomers call an open cluster, a loose, gravitationally bound grouping of stars, born from the same cloud at roughly the same time. The Pleiades, visible to the naked eye on a clear night as a small hazy patch of blue-white stars in the constellation Taurus, are a young open cluster, their parent cloud mostly dispersed by the energetic young stars within it. The Orion Nebula is an even younger example, a cloud still in the process of being lit up and pushed apart by the hot young stars that have recently ignited within it. These are the nurseries caught in the act. The molecular clouds, mid-delivery, their most recently born children blazing away inside them. Over the billions of years ahead, the gentle gravitational tides of the galaxy will slowly, inexorably pull the members of this young star cluster apart. They will drift away from each other, each heading off on its own long journey around the center of the Milky Way, separated by the vast distances of interstellar space into individual stars, no longer clustered, no longer connected, except by their shared origin in the same long-gone cloud. Some will live for tens of billions of years, burning quietly and slowly, outlasting their neighbors by epochs. Others, the more massive ones, which burn their fuel at a prodigious rate and live correspondingly shorter lives, will exhaust themselves in a few million years, puff up into red supergiants, and end in supernovae that scatter their hard-won heavy elements back across the galaxy to seed the next generation of molecular clouds, the next generation of stars, the next generation of worlds. The cycle turns. It has always turned. It will always turn. But in this particular moment, in this particular corner of the galaxy, a new star is simply burning, quietly and steadily on the main sequence, warming the space around it, slowly nurturing the early formation of worlds in the disk that still surrounds it, being, fully and completely, what it was always becoming. The universe is old, 13.8 billion years old, give or take 100 million or two. In that span of time, across the hundreds of billions of galaxies that populate the observable universe, it is estimated that something in the range of 1 to 200 billion trillion stars have been born. That is a number with 23 zeros after it, a number that exists only as a notation that cannot be intuited, cannot be imagined, cannot be held in the mind in any meaningful way. Every one of them was born the way you just watched, not instantly, not by any divine shortcut, but through the long, patient, unglamorous, extraordinary process of a cold cloud collapsing under its own gravity, of a protostar feeding and growing in the dark, of a threshold being crossed, of a fire being lit from the inside out. Every star, every single one. But perhaps tonight, you felt just one of them. One cloud, one long silence, one tremor that tipped the balance, one protostar growing warm in the dark, feeding through its disk, announcing itself through jets of fire. One threshold crossed, one moment of ignition, one star stepping out of its cocoon and into the light for the first time. That is enough. That is, in fact, extraordinary. That is everything. Because the universe does not become more meaningful in proportion to how much of it you can comprehend at once. It becomes meaningful in the single story, the single cloud, the single star. The understanding that behind every point of light in the night sky is a history as long and as improbable and as quietly astonishing as the one you have been listening to. We are, as a species, very new at this, the first human to understand what a star actually is. Not a divine light fixed in a crystal sphere, not a hole in a dark vault through which the light of heaven shines, but a ball of gas held together by gravity and powered by nuclear fusion, lived within the last 100 years. The first person to work out the proton-proton chain, to trace the nuclear pathway from hydrogen to helium, and show how the sun generates its energy, was Hans Bethe in 1939. Less than a century ago. In the long context of human history, this knowledge is newborn. And yet here we are, with that knowledge, in the middle of the night, listening to a story about the birth of a star and finding it not cold or clinical or merely technical, but genuinely, deeply beautiful. That response, that sense of wonder at the mechanics of the cosmos, is not separate from the science. It is part of it. It is what drives the science. The curiosity that makes a physicist stay up late calculating the temperature at which hydrogen nuclei fuse is the same impulse that makes a person look up at the night sky and feel, for a moment, connected to something larger than themselves. We are the universe, looking at itself, not metaphorically, literally. The atoms in your brain, tracing the circuits of thought and memory and wonder right now, were made in stars. The question forming in your mind about the nature of the cosmos is being formed by the cosmos itself, understanding reaching back toward its own origin. Tonight, somewhere in the Milky Way, possibly within a few hundred light years of the spot on Earth where you are lying right now, a molecular cloud is beginning to collapse. A new protostar is forming in the dark, growing warm in its cocoon, beginning the long process of becoming a star. You will not see it. It will not know you. In the vast indifference of cosmic scale, you and it are not acquainted. But you know it is happening. You know now what it is going through. You know the cold beginning, and the long silence, and the tremor, and the disk, and the jets, and the hidden warmth building toward a threshold. You know the moment of ignition. You know the steady burning that follows. You carry that knowledge with you now, into sleep, into the ordinary dark of an ordinary night on an ordinary planet orbiting an ordinary middle-aged star in the outer arm of an ordinary spiral galaxy. But none of it is ordinary, not even slightly. Sleep well. The stars are being born, and they will still be burning when morning comes.